Good morning. This is also a topic uh, from fluid mechanics. Now I am going to talk about rotational and irrotational flows. For the study of this topic, rotational and irrotational flow, writing is required somewhere on board or any page. But without writing, this is also possible. I am just now going to deliver a lecture on this topic, rotational and irrotational flow. Just I want to develop the idea. Okay. The required mathematics you will get from book, from any book you will get the required mathematics. It is very easy. You know rotation. Earth rotates around the sun, moon rotates around the earth. Moon has only one motion. It rotates only around the earth. Around its own axis, moon does not rotate, but earth rotates. Earth rotates around its own axis. Again, it rotates around the sun. Okay. So, in fluid flow problems also, such phenomena are there. You know translatory motion. You know curvilinear motion. In engineering mechanics course, you have studied all these things. In the part dynamics, you have studied rectilinear motion, means motion along a straight line. Then curvilinear motion, motion along curved line, motion along a plane, motion in three-dimensional space. Everything you have studied in engineering mechanics course. In fluid mechanics also. This is also a mechanics course, but this is mechanics of fluid, means mechanics of liquid and gases. Liquids and gases, okay? So, I just now want to develop the idea of rotational flow. And if the flow is not rotational, then the flow will be called irrotational flow. And this thing will be tested at each and every point of the fluid domain, not on only one point. At each and every point on in the flow domain. Okay. In three-dimensional space, you know that any coordinate axis, any coordinate of point is denoted by three coordinates, x, y, and z, if the flow is three-dimensional. And we are now going to talk about three-dimensional flow. The most general flow is three-dimensional flow. X, Y, Z. So if the expression is known, expression for rotation, if known, then at any location x, y, z, if all the three components are there, three rotational components are there. Rotational components are three. Around x-axis, that component is denoted by omega suffix x around x-axis. Okay. Around y-axis, it will be denoted by omega y, and around z-axis, it will be denoted by omega z. Right? You have to check whether all these three components are simultaneously zero or not. If all these three components, omega x, omega y, and omega z, all these three components of rotation vector are zero, then only you can say that the fluid flow domain is irrotational. What means not rotational? Irrotational means not rotational. Okay. And if any of these three fluid flow rotation vector has three components, omega x, omega y, omega z, if any of these three is non-zero, then the flow field will be called rotational. Okay. So components are denoted by omega x, omega y, and omega z. Now I am trying to explain what is rotation. Say if you take this stick, okay, this wooden slab, if you take and say this is executing this motion. Say first, now this is kept in horizontal position in my hands. Means this is parallel to the floor of this room. Okay, so this is horizontal. If this is rotating this way, means at any instant of time, at any location, this remains parallel, this wooden slab remains parallel to the horizontal surface or parallel to the floor. You can see this is rotating, but it is this is executing a motion around a circle or around a closed path. Okay, but at any instant of time, at any location of this wooden slab, this remains parallel to the horizontal surface. Then we will say that this is not rotating, means with respect to fluid mechanics, this will be called that this stick or this straight line is not rotating around its own axis. Rotating, but it is not rotating around its own axis. Okay, which one is the axis? Which one is the axis? It is executing this motion on this plane, on the plane of my palm. Okay. So, which one will be the axis? Axis will be perpendicular to my palm. Perpendicular to my palm. Okay. This will be the axis. Around this axis, this is not rotating. Okay, around this axis, this is not rotating. Again, say the initial position was this, like this. And so now suppose this is parallel to some one line. You take one reference line here, somewhere here, anywhere. Position is arbitrary. Somewhere here you take one reference line. And suppose initially this is parallel to that reference line. Suppose that reference line is this hand. Okay. And it is executing motion in such a way that at any instant of time, this remains parallel to my hand, means to this reference line. Then also, this is non-rotational case. And except for this case, any other cases are the cases of rotation and flow. Okay, so in case of fluid flow problems, what is done? It will be easy to understand if you take two-dimensional fluid element. Then it will be easy to understand. Suppose on the plane of paper, you draw two axes, y and z, and x will be the perpendicular axis. Means perpendicular to the plane of the page. That is the x-axis. And now you take one rectangular fluid element. A rectangular fluid element. Again, this is a control mass system case, control volume case. This is not control volume case. This is a control mass system case. Okay. Now, since fluid flow exists, that means with time, okay, with time, the position of the control mass will change. So, after time delta t, at any instant, when t was equal to 0, you have taken one rectangular fluid element. And now you consider two adjacent edges of the rectangle. Adjacent edges, okay. And after time delta t, you check whether the angle between the adjacent edges, what is the initial angle of the adjacent edges? Since it was a rectangle, so adjacent angle was 90 degree. Right? 90 degree. Now after time delta t, the position will be different. Position of the same fluid element will be different. And maybe the fluid element no longer be in a shape of a rectangle. The shape may change because each edge is having some different velocities. Each edge of the rectangle has some different velocities. This is the most general case. Since velocities are different, then after time delta t, the angle between the adjacent edges may change. If angle changes, if the angle no longer remains 90 degree, then we will say that the fluid element is rotating. Then we will say that the fluid element is rotating. And if angle remains same, initially it was 90 degree, after time delta t it remains again 90 degree, then we will say that fluid element is not rotating. Okay, fluid element is not rotating. So three components are there. When you are taking YZ plane of the paper is called to be here YZ plane, then omega x means component of the rotation vector along x-axis. That omega x is given by, if you follow book you will get there, omega x is equal to half into half, then start bracket, within bracket will be del x del y, omega x del y del z. So del w del y del z, del w del y minus del w by del y minus just the opposite. In the denominator will be I am getting confused. I am telling you the way to remember this formula. Omega x is equal to half into, first you write the denominators. Omega x is equal to half into, start the bracket, and in the denominator write delta y and delta z. And in the numerator write just the opposite velocity components, delta y, delta z. So in the first position write delta w, and in the second position write delta v. Right? Delta v. So what the component becomes? The second component is delta v by delta z. Delta z x, y, z. Delta y, delta z. So delta w, delta y, half into delta w by delta y minus in the denominator delta z and in the numerator delta v. Like that. Similarly, you can write omega y and omega z also. Okay, when you are writing omega y, then write first in the right hand side, write half, and in the denominators you first write delta z, delta x, and in the numerator you write components of velocity just opposite to these directions. Okay, so delta omega y is equal to half into, within bracket in the denominator, delta z, delta x, and in the numerator delta u and delta w, like that. Similarly, omega z is equal to half into, in the denominators you write omega z, so omega x and omega y, so in the numerator delta v and del u, del v, del u, like that. So you know all these rotation components, and you know that vorticity vector is just twice the rotation vector. Okay, you just multiply by 2 the rotation vector, you will get the vorticity vector. So either you can check vorticity vector or rotation vector. If rotation vector is 0, when rotation vector will be 0? If all these three components will be 0, then only rotation vector will be 0. If rotation vector is 0, then only the fluid flow problem, given fluid flow problem is a case of irrotational flow. Otherwise, rotational. That was the idea behind this analysis, okay? And this is necessary, why? Because just before starting your calculation, if you know that the given fluid flow problem is irrotational, then the equations will be somewhat easier to solve. That's why these concepts are used. Anyway, that thing will be discussed later in separate video, okay? Just in this video, I want to make you understand that what is the difference between rotational and irrotational flows. Okay, always you have to check this way mathematically. Okay, this is the end of this lecture. Thank you.